Marco. Marco will talk about the Zakharov-Shabat spectra and the minimal Dirichlet energy problem. Speaking of yours.
Okay, thank you. Thank you very much. It's a pleasure and honor to be invited to speak here. And so people that know me would expect something else, right? Something about Riemann-Hilbert. There would be no Riemann-Hilbert here, and not even spinors, I'm afraid. I'm sad to disappoint this. Ken is leaving because. All right, so okay, to start something that everybody here is familiar with, focusing nonlinear Schrödinger equation is this nonlinear PDE for a complex valued function, and which we are looking at it in 1+1 dimensions, right? So what we are interested in is this average intensity, as it's called, which is the essentially the average of the L2 norm. You see, if I take this limit and this is L2 square summable, then well, would be zero, right? Average intensity. So we are clearly interested in solutions of the fNLS, which are not square summable, quasi-periodic typically. Okay, and so that this limit exists, and of course it's easy computation using the differential equation that this limit, provided it exists, is time independent.
Marco, we have trouble seeing the bottom slide back here. Is there any way to get it up a little higher? Yeah, there you go. That's it. Thanks.
Okay, so right, so that is our average intensity, and there are plenty. This is an integrable PDE, right? Nonlinear PDE. It's integrable by the inverse scattering method or Zakharov-Shabat method. And we are particularly interested in the subclass of exact solutions, which are called the finite-gap solutions. That history goes back deep, the 70s, right? Matveev, Eads, Dubrovin, and many others. And these finite gap solutions are constructed in terms of Riemann theta functions associated with a real hypermetric Riemann surface. Well, this is in a way the Riemann surface R that covers twice the complex plane. So here's the depiction. So you fix some endpoints of bands, B1, B2 in the upper half plane. And the fact that it's a real hypermetric simply means that the other half is symmetrically located with respect to the conjugation. And if I have G+1 endpoints of bands in the upper half plane, the genus of this Riemann surface is G. Okay. Now you can think of the Riemann surface as the Riemann surface obtained by you slice the plane amongst them vertical cuts, take two copies and glue them along these cuts. But don't be too tied up with this imagery, because the choice of cuts is arbitrary. And actually it's good to keep in mind that you can deform the cuts in many different ways. So the solutions that are constructed out of these data, they are finite gap, also called quasi-periodic, meaning that with respect to X, they are either periodic strictly, so if you choose them in some Diophantine way, or quasi-periodic, they tend to repeat, both in X and Y. Now, we are not interested so much in the T dependence, we're interested in the X dependence. And so I want to introduce the notion of spectrum of a so the spectrum of a solution of Q of fNLS, or actually the spectrum of some function Q of X is obtained as follows. So first of all, let me remind you.
That's convenient.
Yes, convenient, right? It can be dangerous, right? Because then you are in harm's way. So the origin of the integrability study of this fNLS is the compatibility, expressing the fNLS as compatibility between two PDEs, first order PDEs, and here it is, right? So you choose your Q of X and T. So this one does not contain derivative with respect of T. So here T is just a parameter. So just choose the Q of X in a suitable class. And then construct this matrix depending on the this is not division, right? This is complete conjugation. It looks like Z over, but this is not. This is the complex parameter. We call it the spectral variable in the complex plane. And then solve this first order ODE, which is a Dirac equation for the known vector psi or matrix, if you want to do the fundamental solution. So if you also introduce this second equation, right, written here, I'm not going to spell it out for you, you can read, which is a differential equation with respect to T, and you impose the condition that these two equations are compatible with each other, namely that psi is a function of X and T, it follows that Q must solve the fNLS as a result. It's a simple linear algebra, it's almost linear algebra to sense. But here I'm going to discard completely the second one, right? We are interested in the first equation. And so what is the spectrum of this equation? Of course, if you have some, what I'm going to call the spectrum, it's not necessarily the bound states, etc. It's a little bit, it's written here, you've probably read it already. So I'm going to find is the set of values of the spectral variable Z for given function Q of X, such that the supremum of the entries of the solution of psi is over X, as X ranges on the real axis. It's like Yoast solutions, right? You want to find for which values of Z there exists a Yoast solution which is bounded both ways. And the supremum is bounded for given Q. T dependence is immaterial, so I'm not even going to write it here, right? If this is valid at some time T, it's valid for every T. Okay, questions? All right, so clearly the real axis part of the spectrum. Why? Quite clearly, because if I put Z real, this matrix is unitary. And so this is just saying that psi will be an element of the unit, sorry, it's an anti-emission, it's emission. And this is saying that psi is just an element of the unitary group. So it has to be, the entries have to be bounded for every X. Okay, so that's the non-interesting part of the spectrum in this sense. But if I choose a given Q of X is again independent, I put T that I could have omitted. We may have part in the Z variable plane, in the spectral plane, that are not in the spectrum that are not not real. And I want to immediately note that if Z is in the spectrum, Z bar is in the spectrum, right? Using the consequence from the equation. So I'm going to all the spectra that I'm going to draw them all in the upper half plane because the lower half plane is just the top. So the first question, what is the spectrum of a finite gap solution? Seemed like a natural question. I couldn't properly find it in the literature, right? But maybe somebody here can tell me otherwise. So what is, in this sense, what is the spectrum of finite gap solution? The good thing about finite gap solution is that you can write the solution psi explicitly, right? And then it's a matter of checking on the explicit solution for which values of Z that thing is bounded. So, sorry, it's explicit. It's written in terms of theta function. I'm not going to write out the complete formula. Here suffice to say that the general structure, okay, T again, not really important, but for completeness, right? So the solution of a finite gap Zakharov-Shabat problem. So if Q is associated with a finite gap solution. As a matrix here, which I didn't write out explicitly, if the matrix is dependent, of course, on X and T and Z, depends, of course, on the number of dimensions. And these matrices contain some theta functions and etc. But the only important thing to know about this matrix is that just on the nodes, it's bounded with respect to X for any fixed Z. Uniformly of the contact set with Z.
Could you say again, what are you taking your definition
For spectrum?
of a finite gap solution?
Well, I didn't properly define it. It's the finite gap solutions associated with the hyperelliptic Riemann surface with those, the standard formula, if you know it, but it's like the KDV finite genus Riemann surface, but it's not KDV, it's NLS, similar type of formula. Yeah, I didn't write it, but yeah.
It's not defined as the solutions that have a finite number of bands where the spectrum is.
Well, but for focusing is not the same. For defocusing, you may define it that way, right? But for the focusing, you don't know where, because the spectrum is not real. You don't know where the spectrum is. So there's a big chicken and egg. In that sense, it would be chicken and egg, right? So if they were focusing, then the problem is that if adjoint, the spectrum is real, the bands are on the real axis, then you can exactly define it in that way.
But you don't need to know exactly what spectrum means, that just generally the branch point.
Yeah, so in general, these formulas in the literature, the formula of each, etc., the input is just the branch points. That's it. And then out of that is a procedure. You construct the theta function, and here is the formula, and that's it. So that's the formula that I'm hinting at here in a Greek way, right? This is some theta function. Now I'm just muscling my way to convincing you that saying that this one is bounded with respect to X. Believe me. So then there is this thing, right?
Sorry, just to make sure the data which you take
Branch points.
is just the branches. You got a finite number of branch
Yeah.
points off the real axis.
Correct. Well, it's the same data as KDV, right? So you just need to know where the endpoints of the bands are. It's just that the symmetry is different. They are vertically symmetric.
And there's phases, right?
Oh, yeah, sure. Then you should put some phases, but that's just, so then you're right. So I would have to, some initial data, there's a genus, there's a G parameter families associated with, but so irrespective, these things will remain bounded. Now, the important thing is this exponential part. And I'll tell you in a second what is P and Q. So this is called the quasi-momentum. This is called the quasi-energy. The quasi-momentum depend only on Z as well as quasi-energy. But here is multiplied by X, which is our main focus. And this is multiplied by T. So now think a second, right? So this remains bounded for any X. The question whether this is bounded now falls upon the question whether this is bounded for every X. So for positive and negative. So clearly, if this P of Z has any imaginary part whatsoever, positive or negative, one of the columns of this, will either the first or the second, will be unbounded for X positive or X negative. Okay, so even without knowing what is this P at this moment, it's easy to say, as we see, that the spectrum coincides in. Okay. So this is what I said without. Yeah. So that relies upon only the imaginary part. X is real, so plays no role. So this is in the end the outcome of the spectrum. Yeah.
Sometimes when you normalize your differentials and so on, you build the theta function solution, this W factor might be unbounded in X, couldn't it?
No, because of the symmetry of the Schwartz symmetry, because it's a real curve. In the end, it's always bounded. Next.
So
So
don't you have to choose your cycles also to be symmetrical?
Oh, no, the cycle choice is purely instrumental. The solution does not depend.
Yeah, the
on
whole
the
thing
cycle.
doesn't, but what part of it is W and what part of it is quasi-momentum does depend?
No, it doesn't. Yeah, that's a good point. Because, so, okay. Maybe it does, right? But so the cycles, you choose the vertical one. The A cycles are the vertical ones. And then the quasi-momentum is normalized to be zero on the A cycles. But that seems to be cycle-dependent condition. But because of the symmetry, that condition is equivalent to saying that all the periods are purely real. And that because of the symmetry, the A period, the vertical, sorry, this is kind of inside information. The vertical period would have to be imaginary. But so if you are asking that they are real, then you're asking that the A periods are zero, but then as the effect, also the B periods are real. And that condition is independent of the choice of alpha and beta cycles. So the correct definition would be that this is a Boutroux differential, is the unique, I'm going to get there. Okay, so what is P? What is P? These quasi-moment, same thing applies to quasi-energy. Is the abelian integral of the following differential, right? So it's something that looks as follows. In the denominator, you have z, right? In the numerator, you have some polynomial of degree 2g plus 2. What? G plus 1. Sorry about that. G plus 1, right? Okay. And how is it chosen? It's chosen in this way, right? So what did I do?
Maybe connection.
No, this went to sleep. Okay. So I have to keep them both awake and the audience. All right, so okay, so right, so the A period which I've chosen as this vertical cycle, I want them to be real. Now, but if you look at the structure, this would be a real polynomial. This period vertical would have naturally come out to be imaginary. So that implies that they are zero, right? But so these conditions, yeah, okay. And the quasi-momentum is just the integral from one of these branch points. Of course, well, let's say this one, right? To z, avoiding the branch cut of the platform of these differential. And it has the polynomial as these, again, 2g plus 2. Sorry, as this structure, right? Okay, so we also have to impose this coefficient is necessary because we want to have no residue at infinity. And the other coefficients are fixed by these conditions. There are G conditions there, complex conditions, right? All these integrals are zero, and there are G coefficients in this state. This is the G minus 1. Okay, so okay, so that's I already said. By definition, then a different way of phrasing the same thing, the standard. This is just the standard solution, right? dP is the unique differential without residue infinity of this form that starts 1 plus order z minus 2 dz, and satisfying the Boutroux condition that all the periods, all the integrals along any closed path, so this is fancy language for any closed path on the Riemann surface, all these integrals should be real, right? And that's not, it's not a condition that depends on choice of alpha and beta periods. So same thing applies for Q, but not important here. So So as a consequence of these Boutroux conditions, I think this is better if I move the other side.
So those are conditions on the branch points, is that right?
They are, well, no, the branch points here are independent. These are conditions on the numerator of this expression, right? On this polynomial. These B you choose wherever you want, and these condition determines uniquely the numerator. That's it. And if this is linear algebra, you can always solve as well. Later, we have what you are looking at. Okay, the fundamental property is that with the Boutroux condition in place, well, of course, P is not single valued, right? But the imaginary part is, because if I do analytic continuation on any path, only because the only periods are real, only the real part is not single valued. The imaginary part is single valued. And not only it's single valued, it's harmonic because it's the imaginary part of on the Riemann surface. So I'm not talking about the plane, I'm talking about the Riemann surface, right? Itself. So it's harmonic everywhere except at infinity. So, well, this is already repeating what you said, right? So now, then we ask, okay, I want to find imaginary part P equal to 0. I had explicit solution, and here is how it looks like, right, for example. So these are the B, you can read B1, B2, B3, B4. So it happens, but this is not a generic situation, that one of the zeros of the numerator coincide with one of the poles. So it effectively is a square root in the numerator. And then you have the spectrum forming these kind of Y shapes. So these arcs are uniquely determined, right? Other than that, because this is the imaginary part of P is well defined on the Riemann surface. You may say, but okay, but this is the plane. Yes, but if you look at the imaginary part on one sheet or on the other, it just changes the sign. So the zero level set, well defined, it gives these curves. So for people in the business, they may recognize that these arcs are the trajectories of the quadratic differential, more about that later, which is a fancy way of saying the square of dp. And they are defined by the condition and imaginary, so they're curves such that their tangent, z dot squared as a complex vector, multiplied by q is identically real. Okay, so the imaginary part is constant along those lines. So this is instead how it looks at generic situation with branch points, right? So B1, B2, etc. So of course you have to imagine this doubling, right? The spectrum is doubling. So you have, for example, here the blue is the spectrum. The arc will make B1, B2, B3 connected with B3 bar, B4 also. This is the fourth leg, etc. Okay. So that's what we call the spectrum of a finite gap solution, right? Again, it's a zero level set of the quasi-momentum, of the imaginary part of the quasi-momentum, defined from that. So to the question of Peter, if you had chosen a different set of A alpha and beta cycle, yes, the quasi-momentum would take a different phase, but the theta function also would take difference, and then because of the transformation, in the end, the formula cannot depend, right, on the choice, right? So we are saying, well, let's choose this, then you have a nice interpretation of quasi-momentum with this Dirichlet energy, which is also closer to Wheeler type of considerations, right? Because the quasi-momentum should have purely imaginary. Okay.
Mark, was that is this a numerical plot? Or
numerical plot, yeah.
And does the blue curve coincide with the real axis? Sort of.
Sorry, yeah, here on the real axis, the code is finicky. The real axis should be always blue because the whole. Now what maybe it's good if I point out some feature, right? So there are some green dots here, right? So these green dots here, I call them, for some reason, stagnation points. They are stagnation of certain vectors. These points on the, so whenever your spectrum hits the real axis and then goes down, these, oh, sorry, what are these green dots? They are simply the zeros of the numerator. Right? There are this numerator has G plus 1 zeros, generically, simple, right? 1, 2, 3, 4, 5, 6, genus 6. Some of them may be real, and some of them are complex, but then of course there is a complex conjugate. Okay. And these ones that are out of the real axis, let's call them stagnation points. And that's more or less how it looks. It's not for you to choose. Well, once it fits the B's, the curves are uniquely determined, right? So I cannot choose to connect this and that. And it's then would make sense to choose the branch cut of your inner surface following those curves. But it's not really. Okay. Sorry.
Wait, choose the branch cuts of which Riemann surface?
Of your square root of dp, right? When you construct the branch cut, you can choose however you want. So it would, it's in some sense, it's convenient to think that the branch cuts are exactly running along the spectrum.
Yes.
But
This
it's,
was
I mean,
constructed with a different choice of branch cuts.
that is, yeah, right. But the branch cut do not affect, right? Okay.
Sorry, Marco, this, just to double check my understanding, it's so this, the blue curves are solutions of the equation in yellow, so this is a
Correct.
quadratic differential.
Yeah,
And
that's it. Well, the ones that start from the red dot,
From the
because of
red,
course
yeah.
you can choose an edge. I'll have nice pictures. Okay, so what about Dirichlet energy here? So it turns out from the formula, right, explicit formula of finite-gap, that if you expand your quasi-momentum differential at infinity, this coefficient on top of z square is precisely the average density, average intensity. Okay, so you can write it all this way, or you just say that it's the residue at infinity of z times the quasi-momentum differential. So for convention, so because sometimes some of the zeros of the numerator may hit one of the poles, and then it's a zero in the numerator. Let me denote E1 through En, the branch points that are really in the denominator, right? And then the rest will be some. So in general, your quadratic differential will have to look like that. So z minus z. Well, these are the poles. And here's some polynomial of degree 2n. Now, what is the quasi-momentum itself is the square root of this expression. So what is the genus? Well, it's depends on how many odd zeros will happen to be there, right? But I'm not fixing the genus a priori. We only demand the Boutroux condition, or the same Boutroux property that we had before. So, yeah, so that every period on the Riemann surface, the genus, here, right? Right, so the genus, so this is the quasi-momentum for some, if under this condition is the quasi-momentum of some finite-gap solution of genus, what? N minus 1 coming from the denominator plus the number of odd zeros that happen in the numerator. Even zeros do not contribute to the genus, right? They take square roots. Okay. Right, so there, but I want to reserve a special attention to these sets of. First theorem is this. So by F, I denote the part of the spectrum which is not the real axis, the interesting part. So this blue, well, what you see here in the picture. First theorem says that the intensity, the average intensity, given the formula, is also the integral over all of the imaginary part of W over a measure supported, a positive measure, supported on this set F. And this positive measure, of course, is what can it be? It's just this, right? So here is absolute, there should be absolute value. So in other words, it's the absolute value is just up to the factor of pi is the absolute value of the quasi-momentum. But along the curve, along that particular set, right? Not any other set. So the trajectory. It's more or less Cauchy residue here. There's nothing particular. So where the second part of the theorem that the spectrum is actually in the terminology of quadratic differential is the union of the critical trajectories that come out of the simple zeros, sorry, the simple poles, namely the e's, and every possibly odd zero from the numerator, so something like that, for example. Yeah.
What's the left-hand side? What's I of F?
Is the average intensity that I defined in the beginning, is the integral. So I of F, so the notation is it's I of the Q, right, of the finite gap solution is the limit of L goes to infinity of 1 over 2L, the integral of mod.
Okay, sorry about that.
Okay, so this is where you start smelling Dirichlet. And that's not a nice way of saying. Okay, so the second theorem is as this, right? You can, if you write the imaginary part of quasi momentum, you can write it, subtract the imaginary part of Z and call G what is left. Okay, according to this. Then restating the rest of the properties. First is that G is continuous everywhere in the upper half plane. It's harmonic except on the spectrum F. When you restrict it to F is equal to imaginary Z, and of course when you restrict to the real axis is 0, right? Because everything in P is 0 on the real axis, and this is 0, this is also 0. But this is a Dirichlet problem in harmonic analysis. The most vanilla type, right? Give a set, give a function, boundary value of harmonic function on the set, on that set. And the other, as a consequence, can rewrite the same average intensity as this expression, the integral of the norm square of the gradient of G, which is called Dirichlet energy. Okay, so now we'll explain how the average intensity for finite gap is interpretable as the Dirichlet energy of this solution of this Dirichlet problem. So the question is, do these have some extremality property? Now we are connected with some energy problem.
These two theorems is new results, right?
Say it again?
These two theorems is new results.
I want to say yes, but the literature is vast, and sometimes what you think it's new is not. But yes, as far as I'm concerned, it's probably new. It's not very difficult. It's probably some. Well, the reason why it may not be in the literature is because people may not have looked at what is the spectrum of a finite gap solution, right? But the moment you start getting into that frame of mind, is the inevitable chain of thoughts. It's ChatGPT 5. Okay, so do they have an extremality property? And the answer is yes, right? So they minimize the Dirichlet energy, provided we define where we minimize, right? Always redefine things. Okay, so switch gears for a second. Let's talk about this generalized quasi-momenta. Why we call it quasi-momenta would be probably clear after Talet's talk, when you solve the NDRs for gas of solid things. So take an arbitrary compact set in the upper half plane. Star means arbitrary, but what? Nice. Should be nice in the sense of harmonic function theory, right? So it should not have thin points in the sense of Dirichlet type of problem. Okay, then what do you do? Here is the problem, is just parrots the problem we just saw, but for an arbitrary set. I have a my set K, and I just restate the same problem with just K now is you choose K. Okay? So G should be continuous, should be harmonic, imagine restricted to K should be identical in Z, imaginary Z, and exactly Z. So again, little exercise in harmonic function theory. Turns out that G you can write as the integral over a measure, which actually turns out it's supported only on the outer boundary of the set. So in this kind of problem, there is an outer boundary, so I can write here.
Yes.
That feels strange. I feel like a graffiti artist. No? So if I have a set that looks like this, but with a hole, the outer boundary is this, right? This is not this is the boundary of the set, so K is there. So that's what I mean by outer boundary. It's the boundary of, it's called the polynomially convex closure. Anyway, it's supported on the outer boundary. It's measured, that's why, but in general boundary, all the Green's function of the half-and-half plane. This is the standard Green's function. And the generalized quasi-momentum we can define similarly, right? So in such a way that, so Z minus I times this G, and this H is just the harmonic conjugate to G. You may have gotten the, no, it should be correct. No. Okay, signs are a big option. Okay, this is the harmonic conjugate. So G is single valued and continuous real valued. H is real valued, but it's not single valued in general. If the domain, if the complement of K is not simply connected. Okay. So the consequence of this formula is that you can write the expansion of this quasi-momentum at infinity. This drops immediately from there, right? This is the second coefficient. So before we had dz, sorry, z squared, but it was the differential. So this is the antiderivative, right? But I think I may have the off by here. There should it was a constant. Yeah, okay. That's not important. We're interested in the blue part. Okay, so. And that, again, some exercise shows that, again, this thing is the same as the Dirichlet energy of the same G. So, same thing happens. But now K is arbitrary, right? You are allowed to modify your K. So, for given K, the measure, the connection with NDR tomorrow of Alex is in this here, right? If I choose K complex, and this as I construct the measure according to the solution of the Dirichlet problem, blah blah blah. This measure also is the unique positive measure that minimizes this energy function. So this is the standard Green's energy minus the external field. Okay, and this gives you the desired connection to the nonlinear dispersion relation that Alex will talk about tomorrow. This is the plugin for tomorrow's talk. Now, of course, the notation, I not by chance, I denote by I or K, because if K is equal to our F coming out of the quadratic differentials of the two condition, of course, it's the same, right? So then this generalized quasi-momentum becomes the quasi-momentum of a finite-gap solution. What about the extremality properties? Okay, so there is a vast literature. Yeah.
So, what is the support of these measures? You got to assume something about the support to make.
Oh, so measure supported on K.
Remind me what K was.
K, you choose compact. So you choose K, find all measure, choose all positive measures on K, and minimize in that class the energy function.
Could you describe again, there's a circle that connects to the
Average amplitude.
Yeah.
I'm ChatGPT-ing Ken. No.
It just didn't follow, so if you have, instead of taking a fixed K, if you choose the K that comes from the
If you choose the K that comes from the construction of Zakharov-Shabat finite gap, then the two definitions coincide because they solve the same Dirichlet problem.
Yeah, but did you mean by that you choose K to be the spectrum?
Yes, you choose K to be the spectrum and the measure will come out of the solution of the Dirichlet problem or the minimization, which is equivalent. Okay, so these extremal problems are extremely common in the literature, but they are usually in the literature about quadratic differential and goes back to, Birch, 1928, Miller, 40s, Jenkins, 60s, Schiffer, Strebel, Kuzmina, late 90s, Strebel, 80s, Schiffer, maybe 50s, 60s. And there was a great motivation because they were using, to study incompressible flow around airfoils, right? You have to solve this type of problem, and that's where the terminology stagnation point comes in. So two-dimensional fluid flow. Now, the main inspiration comes from this paper of Jenkins, but he's discussing not the same energy problem is logarithmic energy or minima capacity. And there are also, I want to refer to other papers that I forgot, very bad omission is Zhenya Rachmanov, right, in his group, Kuzmina, Stahl, Pilar, Silva, etc. So I want to state properly this minimization, right? So I need to understand what is the orthogonal flow. Here's the picture and 1,000 words that go with the picture. So here is an example of one of these spectra. Okay, and these lines are the gradient lines of G. Okay, G, and whereas this green line, for example, is a level set of G, and the blue line is also level set of G. Is a level set. Sorry, not of G. Sorry, these are the gradient lines of. So you write P as U plus IV, right? So it was Z minus IG plus H. So V is the main thing, right? So V is essentially G to imagine a part of Z. And the gradient lines of V are these lines. Why they're blue and black? Another reason, right? Okay. So you see that, and the green is the level set. So the level set V equal to 0 is the blue line and the real axis. And this green line is another level set. So try to picture these as an elevation map of a mountain. This is a saddle point. Here is a valley, right, that goes in. There is a very thin lake down there. Here is this thing. This is a river with branches. And then it goes, it mounts, right? There is another interpretation in terms of electrostatic. So suppose that you are living in the two-dimensional world and there is a very highly charged cloud up there. And there is a background field, which is constant electric field, the imaginary Z, right? Electric potential is imaginary Z. And now you have this set and you ground it so that the energy is 0 here. So you're constructing what? You're constructing some kind of lightning rods. Okay, so this is how the electric field after you put the lightning rods will look like these lines, right? Okay. Okay. Now, it's also important, so these orthogonal flow is the flow of the gradient of V, which is, these are the flow lines, right? This is the stagnation point because the flow line that gets there stop, right? And so that's why it's stagnation point. Now, the important thing to state the theorem of extremality is this. So for every Z in F, right, so I choose one point in the blue set, for example, there are a certain number of orthogonal trajectories. So for these flow lines. So for example, if I choose a point here, there are one to the left and one to the right. If you choose the exact tip, there is only one that goes out. If you choose this bifurcation, there are 3, right, which has kind of this separatrixes of these of this flow. But there's always a finite number of them. And generically, is two, one on the left and one on the right. So I denote by L per Z the union of all the orthogonal trajectories starting from one of these points. And here is what I just said, right? But I mean, most important is the generic situation. So, need to interrupt. So, to state the theorem, I need to state this Jenkins intersection property, which means that, so choose a set K, so F is our blue set, right? A set K has the Jenkins intersection property with respect to F if this formula holds, which means that K intercepts at least one of the trajectories that come out of Z. Interactive experiment says there. Okay, so here is, for example, this doesn't work, right? But I could do this. This works, intercepts everything. But I can do something a little bit more interesting. So if I choose something like this also works. I mean, well, I didn't finish. Right, because, and then something else here. Why? Because from this point, well, both trajectories are intersected, right? From this point, only this one, but it's okay. The other is free to escape. Here, right, this one is intercepted, the other one is free to escape, but it's, as long as one of them is intercepted. Okay, so that gives you a huge class of compact sets. And then you can imagine what is the next line, right? You can auto-complete ChatGPT 5.5. So suppose choose one of these Zakharov-Shabat spectra, and let's denote by the super fancy K of F the set of compact sets that have the Jenkins intersection property relative to F. Then, come on. It has to be obvious at this point, right? The corresponding Dirichlet energy is bigger. And the equality holds if and only if K is equal to F. So they are minimal. These remember, this is the Dirichlet energy, but it also, in some senses, Alex will talk about tomorrow, is also the average amplitude of some gas or solidus, right?
Square.
Yeah. So it means that these Zakharov-Shabat spectra are kind of optimal in this sense. They minimize the average amplitude square. And or, which is the same, they minimize the Dirichlet energy, of course, not unqualified, right? It's qualified minimization amongst the sets in this class, which in particular includes every deformation that you may want to do on the set F, as long as this deformation is within the class that has to touch these points E, right? So again, let's look at the picture. The points E are the red, these ones, right? And if you think of any deformation that connects these blue dots in the same, like we usually say, connectivity pattern, right? So, for example, here is one connected component, so I want to have the same one connected component with my K, as long as it touches all these red dots, and so on and so forth. Then you can easily see mentally, well, to prove, of course, that they will satisfy the Jenkins intersection property. You can try to bend the curve to the left or to the right, that's how you would imagine a deformation. And so within that, so in particular, you can say that within this class, at least you could say that these sets have local minima. Okay, whatever that means. So minimality theorem number one, with one. Sorry. Some comments on the proof, of course. It relies on the theory of quadratic differential, and the idea is to view our quadratic differential as a Riemannian metric on the plane by this form, right? So you just take the modulus square root of it, of your dp, and then it's a positive function, and dx squared plus dy squared. Think of that as a Riemannian metric. It says conical singularities at these poles and wherever the zeros are, but otherwise it's a very nice Riemannian metric. And then the quasi-momentum is, if you write it in real and imaginary part, is just flat. This is a metric, it is actually flat, right? Because if you write this metric in the quasi-momentum, it's just literally du squared plus dv squared. So u and v are the two flat coordinates of this quasi-energy, quasi-momentum. And these level set are geodesics, not any geodesics, they're horizontal, so to speak, right? Because imaginary part is zero or constant. And the level set of U are, sorry, the two level sets form orthogonal families of geodesics. So here is plotted everything, right? The orthogonal. Okay, so there is a slight generalization of comparison theorem, which allows to compare things also when you don't have, they're not the Zakharov-Shabat spectra. So a crucial property that kind of defines the spectra is S property. S is a terminology introduced by Stahl, but S stands for symmetry, not star. And this S property is that if you take the normal derivative of V on these points and on both sides, it's equal on both sides. So it's a kind of, you see already, you smell the equilibrium there, right? Okay, so what if they're not equal? So if deform the contour so that this is bigger than that or vice versa. Then we get a generalized comparison theorem. So there are several versions. Okay. Maybe I should hide. Okay, something, right? Because otherwise you go ahead without me. So choose an arbitrary compact set and construct a corresponding generalized quasi-momentum. So as we discussed, right? Suppose that, so now this is not in Zakharov-Shabat, but the average. Now you want to compare the energy associated with K with an energy associated with another K field. We can do that if, for example, K tilde intercepts all gradient lines. For example, right, what you can do, if I have, if my K is this, and the K tilde is an open set that covers, then the energy is for sure bigger. Okay, so that means that if once you want to linearize the energy want to be thin, naturally. Okay, so now suppose that it's thin, it's quasi not thin in the sense of harmonic analysis, thin in the colloquial sense. Suppose a case with one-dimensional curve, right? And then you look at the solution, you look at it. Now we say that the orthogonal flows. From this point, there are two lines, for example, two orthogonal lines. We call one of them dominant and the other recessive. Which one is dominant? Is the one which has the greatest normal derivative of V at the point, right? On one side, because you will have something in imbalance of these two. On one side is bigger and the other is smaller. Go on that side. So that's the dominance trajectory. And the statement is that if K tilde intercepts all the dominant trajectories, then the energy greatly equals. Okay. So of course, if you are in the S property, then you could fall back on the original theorem. And again, some more remark, a proof relates, well, historical remark. Use this length area method that goes back to growth and type Miller. And the crucial map is the uniformizing map, as you may imagine. If you remember how the uniformizing proof, the theorem of the Riemann uniformizing map, at least the theorem I know of, at some point you are minimizing the special coefficients of the Schlicht functions. Same idea, or same difference. So, for example, here, right? If you, this is Zakharov-Shabat, this is a z-plane, this is a p-plane. So I take from the stagnation point, I take the orthogonal flow that it goes on one side to the real axis, on the other side of here, right? For example. And then I slice the plane there. Then on the complement of this plane sliced minus the set, the quasi-momentum is invertible, and in the p-plane it looks like this. So these two sides are the two sides of this slice, right? This bottom is both sides of this piece, and this piece here is the whole shebang here, right? Why? Because all the blue set has to be imaginary p equal to 0, so it has to be on the real axis. Of course, if you played around with the uniformizing map, you shouldn't be too surprised, right? Okay. So this shaded region is the same shaded region there. And so here, this black part of the real axis is the image of the real axis up to here, right? Then you go along the cut, so you go up to here, right? And then you descend again from here to there, and then you start traversing this each way. You reach E1, then you reach E2, right? Then I go back, and here I go back, and then I'm back here. Then I have to go up and down, and back to the real axis, and keep going, and so on and so forth. So the orthogonal in this plane, the orthogonal flow is literally the vertical lines, literal vertical lines. Okay, and the level lines are just the result of this. Okay, sorry, you have 1 minute. So I think I don't have much more to say. So there is a particular case which mimics the famous Chebotaryov problem in the plane, right? We find a continuum of compact connected set of minimal logarithmic capacity. Our version is as follows. So choose endpoints in the upper half plane and consider the following class. That's fancily written. What does it mean? It means that take any compact set in the upper half plane such that it contains these points, number one. Number two, the complement is simply connected. If the complement is simply connected, then the quasi-momentum is literally the uniformizing map in the upper half plane. And the problem is to find, if it exists, a set within this class of minimal Dirichlet energy. And the theorem is that it exists. It is exactly one of those Fs, and here are some pictures. Okay, right? So they're all trees that sprout from the ground because the complement has to be simply connected. It's not for you to choose, right? How it looks is true. It is selected by the two condition. So you choose the red points, which are the E. These are, if you want, I can show you the code, but just to throw random points and then find the solution of the two conditions. And one of them will have to be in that class, so the complements are connected, and you have these nice trees that and forests.
So all these crops have this minimum logarithmic capacity?
They have this not logarithmic, they have, so this is the analog, but not with logarithmic capacity, with this Dirichlet energy. They minimize the Dirichlet energy within certain class, within that class. So, okay. Right, so of course, if you put them far apart, they tend to look more like this, right? Just bare trees. But if you put them together, you get nice pictures like that. So, first one can ask different questions in the spirit of Chipotle. Can you choose the connectivity however you like for a given set of V? So let me just show you. You can read, right? But because I'm out of time, I prefer to show you the pictures. So, for example, right? So here are the same 4 pictures for the same configuration of E. There are 4 points. It's in the same position. Each of these is allowable, is one of these S property sets or Zakharov-Shabat spectra. Of course, this is of genus whatever, right? This is a greater genus, and this is the greatest genus. But this extra 0 is not for you to choose. The input is just these red dots. Okay. So they all have these local minimization property, if you wish, amongst deformation that preserve the same type of connectivity. And amongst these is actually easy to see, but it's not always possible to compare, right? And I'll show you an example. That this one is the one of these 4 of minimal energy, because if you imagine how the orthogonal trajectories and imagine to overlap one of these 2 rays, you see that all these 3 sets have the Jenkins intersection property relative to that. So that one has to be the smallest one. But it's not all, life is not always easy. And here is another example, right? Again, same 3 points, but different solutions. This and that, they're not comparable with the Jenkins intersection property, because you can try to think, right? For example, these trajectories, some of these trajectories will escape without being intersected by this segment. However, this is kind of an numerical experiment, right? They have exactly the same energy. Okay? So these and that have exactly the same Dirichlet energy. Of course, they cannot be compared by the Jenkins intersection property, because otherwise you would have to say it well, right? Okay. One should have to be bigger than the other. And let's see, the last thing I want to say is why should we?
Which one is the actual spectrum of the Zakharov-Shabat operator?
So, now it depends. This is not exactly the same problem, because here, so if okay, this would be the spectrum of the actual Zakharov-Shabat. So if you just say, I have these 3 band points, and that's it. But if you are not fixing the genus a priori, and you are allowing some kind of ghost band spectrum, that would be this, which happens to coincide with the pole, then you have also that. Right? You see that the genus is different here, right? So now I can't count. This is genus.
This is genus 2
and 3, right? Okay. Right. But you can't infer much of it. It's not always the smallest genus that wins. It depends on the place in the point. So it's a bit, yeah. As often happens in algebraic geometry, right? Life is, in the real algebra. So, why this could be interesting? I'm not saying that necessarily it is interesting. I hope it is, but by itself. But why could it be? Well, if you want to do a really thermodynamic and probabilistic approach of solid and gas, of the NDR, etc., that Alex is going to talk about, you may imagine that you want to allow different supports of your NDR spectra, right? You want to be able to move around with a certain probability distribution. How would you choose what probability? Well, a natural thing is some kind of Gibbs energy. Which Gibbs energy? Well, it seems to me that the average square intensity is as good as a candidate as anything else, if not better. And this theorem is kind of telling you that if in some Gibbs-esque ensemble, right, which is hard to define properly because the probability, you have to put a probability measure over spaces of sets, right? And I don't know how to do that. But the exponential factor with the energy, e to the minus intensity, would say that in that hypothetical, heuristic approach, the Zakharov-Shabat spectra are higher probability than others, right? Because they minimize the energy. So, and in the coldest regime, when the temperature goes to zero, you hit one of those NLS. What to make out of that, leave it up to you, because it's one of those slightly defined problems, because the final probability measure on infinite dimensional spaces is always okay. So for that, I have to say that more research and grant money is needed. So give me money. Okay. I'm also crippled. How can you refuse now?
Question.
We have a question online from Tamara.
Yeah.
Where the Dirichlet spectrum is located?
Okay.
Dirichlet spectrum.
The eigen, that I don't know, because
The views?
the views, right? I would, for the finite-gap solutions, well, it doesn't enter the picture. The Dirichlet spectrum does not affect the average intensity. Right, the Dirichlet spectrum for fixed, so the other, for any initial condition that, so it's tying up with Ken's question. Once you fix the band, the B's in the first interpretation, first description, then you have a family, G-dimensional families of solutions. And of course, the Dirichlet eigenvalues, the Dirichlet spectrum, essentially labels the initial conditions of that. But the average intensity does not know about that. So the average intensity is the same for every solution within that family or G-dimensional family.
Generically, because there might be some, some special case of periodic orbits on the torus.
Well, I'm not even sure. I think it's not even generic. I think in general, because the formula is for finite-gap. I mean, for the average intensity is just the expansion of the quasi-momentum, and that's it. What initial condition they all. So the initial conditions of the Dirichlet spectrum would go in here, right? When you solve for the initial condition would go here. But these, the irrespective of initial condition, this part is the same within for the same band endpoint. I'm not sure if that was answering the question, but anyway, Tamara is not here.
Okay, sorry. You can write in the chat, I mean, if it answers the question.
So, do you think there are examples of sort of deformations of finite gap solutions so that the one has the Jenkins intersection property with respect to one parameter family of solution? It looked like what you were using is that no two finite gap solutions, their spectra could have the Jenkins property with respect to each other.
Oh, no, not necessarily. Well, okay. Not necessarily, right? Because, look, I'm not sure if I interpret the question appropriately, but I gave two examples, two pictures, right? So in this case, all the other three have the Jenkins intersection property with respect to that. And actually, these are the only possible solutions numerically obtained, right? So this one intersects all of the events. I hope they can see. So they look very similar here, but they're not identical, right? So, okay. but by the same code, algorithm, or whatever, these two, they are not comparable with each other. So, of course, they have the same, I want to keep the endpoints the same. But if you're allowed to change the endpoints, then I think it's a bit different question.
You could imagine having a deformation where you're changing the branch nodes, but the energy is
Constant.
constant. Yeah.
Well, obviously you can deform keeping the energy constant because you have just one parameter, one energy is one, and the branch points are many. Well, they in that family, no pair has to be comparable, right? But otherwise, one would have to be smaller than the other, right?
But if it's a strict inequality or it's
Strict. And so the equality happens if if and only if it's the same, up to zero capacity things.
More questions? Okay, but when we solve some initial value problem for semi-class elements, like variables,
Mhm.
can avoid. So the problem with the locational spectrum will be kind of unique, it will be given by initial conditions. It will be deformed, but will be at each point in time. The locational spectrum defined by this minimum energy.
Yes, and it doesn't depend on time. Now,
I mean, it's
sorry. Right, so semi-classical is a different, right, so that's a different game.
Locally finite gap.
Right. So when you do semi-classical, it's a different game here, right? Because you're saying, okay, I look at my finite gap solution, where is this? And, sorry, just a second, let me find it. Here. Okay. So here, right? You look at the finite gap solution.
Yeah.
But now you're scaling both x and t.
Correct.
Right, so then, of course, let's say that x and t are proportional to each other by s, right? And then send s to t. Then, of course, the spectrum now feels this thing.
Yeah.
Then it's of course, we are thinking about that, but it's not for given slope, x and t, the spectrum is well defined. But if you change the slope, because this weighs more than that, or vice versa, then you change. But then it's a bit different story because you could go through the script here, replace imaginary z with imaginary z plus z squared with appropriate coefficient. But then some things change. In particular, the measure of the Dirichlet problem is not necessarily positive. It can be positive or negative on the boundary, because why it is positive is because the imaginary z is positive strictly on the upper half plane. So if you start sprinkling in a z squared, imaginary of z squared, then in some regions it may be negative. And in principle, one can imagine even higher versions, right? You start throwing in more and more higher conserved quantities, and then, yeah. But the general, they will all, so let's say in that setting, the best you can hope is to prove that these spectra are saddle points in these dimensions. So if you deform in a certain way, where the support is positive is the minimum, but if you support where the measure is negative, it's a maximum, right? So it's kind of saddle in this infinite dimensional landscape.
Thank you. More questions? Okay, thanks a lot.